Hey guys, Mr. Longbreak here. I hope all is well and that you guys are still staying safe. We finished up our gas law unit, Unit 9, last week, and now we're going to start in on Unit 10, which is thermodynamics. And the first part of that is going to be understanding what a heating and cooling curve is. And many of you have seen a heating and cooling curve before. We're going to kind of review that today. And it is important to understand that heating and cooling curves are dealing with physical changes, not chemical changes. And more specifically, state changes. So what that means is when a substance goes from a solid to a liquid to a gas, or vice versa, a gas to a liquid to a solid. And to understand these graphical representations of what's going on with the particles during these physical changes or state changes, we first have to understand these 6 terms. And these 6 terms will be used with chemical changes as well, but we are going to focus on physical changes today. And so the first term is going to be heat. And heat is the total amount of thermal energy possessed by those particles. And that total amount of thermal energy can be broken into 2 main categories: kinetic energy and potential energy. And so that first component, kinetic energy, another word for that is temperature. And that should make sense to us because we know from last unit that temperature controls particle speed. It controls how fast those particles are moving. And if temperature goes up, that means that the speed of the particles increases, or if temperature goes down, the speed of those particles go down. So one main component of heat is kinetic energy, or in other words, temperature. And a lot of people think that temperature and heat mean the same thing. They don't. Temperature is just one component of a substance's heat, and it's talking about the speed of the particles. The other component of a substance's heat energy, or total amount of thermal energy, is potential energy. And potential energy is dealing with particle spacing. So we're talking about here particles either moving further apart or closer together, and the particle spacing is really what controls a phase change or a state change. So when a substance actually does go from a solid to a liquid, it goes through that process of melting or that phase change. What's happening is those particles are moving further apart. And so potential energy or particle spacing is what really dictates or controls a phase change. And the way that these particles move further apart is that their intermolecular forces break or weaken. We had a whole unit on intermolecular forces, or IMFs, earlier in the year before Christmas break, and we talked about London dispersion forces, dipole-dipole, and hydrogen bonding. You won't need to recall that information too much, but it's just a reminder of what happens at the particle level to allow those particles to space out more. Those intermolecular forces between the particles are breaking or weakening. Okay, so 3 more terms, and this is going to deal with the transfer of that heat energy. So now that we know what heat energy is and its 2 components, let's talk about transferring that heat or energy. And so enthalpy is going to be what we use to determine the total amount of energy that is given off or absorbed during a process. And it is going to be represented by the symbol delta H. That is the symbol for the overall change in heat energy. And heat energy can either be released or absorbed, and that's where these next 2 terms come into play. And we'll use these throughout the entire unit with chemical changes as well. But exothermic processes are where the system or substance that we're observing releases energy to the surroundings. And a good way of remembering this is that exo, that prefix, think exit. Heat is exiting or being released to the surroundings. And so delta H, or enthalpy, or the overall heat exchange, is going to be negative. So if we use this box to represent the system or the substance that we're observing, it is going to release heat to the surroundings. And because it releases heat to the surroundings, it's going to feel hot to the touch. So that's a really good way of knowing whether a process is endo or exothermic is by the touch. Does it feel hot or does it feel cold? If it feels hot, it is an exothermic process. The other process is pretty much the opposite, endothermic. Endothermic, if you see that prefix endo, think enter instead of exit. Heat is entering the system. So therefore, the system is absorbing energy from its surroundings. And because of that, delta H or enthalpy, the overall heat exchange will be positive. So once again, if this box is our system or the substance that we're observing, heat is going to be taken in or absorbed by that system. And because heat is taken in or absorbed by that system, this time it's not going to feel hot, it's going to feel cold to the touch, which doesn't happen very often. Most of the processes we deal with are very exothermic, but a good example of this is something as simple as an ice cube melting in your hand. When you have an ice cube in your hand, that ice cube is the system. It is absorbing energy from your hand, and because it's taking that energy from your hand, it feels cold. And so that's a really good example of an endothermic process. Okay, so now we have these 6 terms in mind. We are going to look at the graphical representation of a heating and cooling curve. Okay, so this is a heating curve, or the graphical representation of a heating curve. And the first thing I want to point out are the axes labels. Here down at the bottom, we have energy, and energy is being added to the substance or the system throughout this entire graph or process. So that's the x-axis, and then the y-axis is temperature in degrees Celsius. And notice here that we do have a few values, and I'll come back to why those values are special or important for this particular substance, but your y-axis will be temperature. Next, let's go ahead and label each phase or state of matter on this particular heating curve. And so at the very bottom, where temperature is the lowest, we have a solid. And then the next diagonal line, we have a liquid there in the middle. And then at the very top of this graph or heating curve, where the temperature is the highest, we'll have a gas. And there is a state of matter above that. It's called plasma, but we're going to just stick to solid, liquid, and gas. Now at these flat lines or horizontal lines, we still have the matter, but the matter here would be not just a liquid or a gas, but both a mixture of a liquid and a gas. And here you'd have a mixture of a solid and a liquid. Okay, so those are the states of matter at each point in time on this heating curve. Next, let's talk about what are those state changes, phase changes called. And so there are 2 represented, or I actually should say 3 represented on this heating curve. And the first one is what happens, or what is it called, when a substance goes from a solid to a liquid? Well, that phase change is called melting. And so the melting point of this particular substance would be 0 degrees Celsius. Then when something goes from a liquid to a gas, that is called boiling. And it can also be called evaporation. And we call that the boiling point or the vaporization point of that particular substance, which for this substance, it's 100 degrees Celsius. And if you didn't know this, this substance would actually be water or H2O, because water will melt at 0 degrees Celsius and it will boil at 100 degrees Celsius. 2 numbers that are very easy to remember. Now, every substance has a different melting point and boiling point, and that's based on the strength of their intermolecular forces. So these numbers will not always be 100 and 0. It's just for the substance water. That is water's melting point and water's boiling point. And there's one more phase change, and that is when something goes from a solid straight to a gas. And substances can sometimes go straight from the solid phase or state of matter to the gas state of matter, and that is called sublimation. Okay, and so an example of each of these, melting, obviously when an ice cube is melting in your hand, boiling when you have boiling water on the stove when you're making pasta or macaroni and cheese, that would be an example of boiling with water. Sublimation, a good example of that is dry ice. Dry ice is actually carbon dioxide, and you can buy it at the store at Kroger. It's also used with ice cream shops a lot of the time, but dry ice will go straight from its solid form to the gaseous form at room temperature. And when something does that, it's called sublimation. Okay, so those are all the different phase changes. And the last thing we want to recognize is what is happening at the particle level during each of these segments on the heating curve. And this is probably the most important piece of this. So the first thing we're going to focus on are these diagonal lines. And at those diagonal lines, I want you to make sure you know that the temperature is increasing during each of these points. Well, if the temperature is increasing, what does that mean for particles? That means that the particles are increasing their speed and the kinetic energy of those particles is increasing. So I'm going to say at these red lines, we have particles moving faster because the temperature is increasing, which means the kinetic energy of those particles is increasing. So during those diagonal lines, because temperature goes up, that means the particles are moving faster and faster and faster, which means their kinetic energy is rising. Now, the tough thing is, what the heck is going on at those segments? Because at those segments, the speed is not changing. The temperature is not changing. So for instance, at this point in time, the temperature is 0 degrees Celsius. Here, the temperature is 100 degrees Celsius. It's not changing, yet energy is still being added. Well, what's going on then? Well, that energy is being used as potential energy. So potential energy is being altered at those horizontal lines. And what about the particle changes when you're dealing with potential energy? Not the speed, but the spacing. So the spacing of those particles is increasing at those horizontal lines. And because the spacing is being altered, remember that is what gives us a phase change. Or in other words, a state change. So as a result, we have a heating curve where the particles are moving faster and faster and faster, and they're also spacing out. They're moving faster at those diagonal lines, and they're spacing out at those horizontal lines to create these changes in state. And so down here in these boxes, I'm going to represent each of these states. So for a solid, we start here. The particles are really close together, and they're not moving very, very quickly at all. So here we have a solid. Well, when something goes from a solid to a liquid, now we're looking at this phase right here, it melts. And when it goes from a solid to a liquid, the particles move further apart. And that is called the heat of fusion. It's the heat or energy that's used to separate those particles from a solid to a liquid. And on top of moving further apart, they also begin to move quicker. And so now we have a liquid state of matter. After the liquid state of matter, we have this point where it boils or evaporates. And that heat that is used to separate those particles even further from a liquid to a gas is called heat of vaporization. And once they space out more, they're going to start to move even quicker. And now we have a gas state of matter. So that is the heating curve. And in particular, it's the heating curve for water because we have 100 degrees as our boiling point and 0 degrees as our melting point. The last thing I want to do before moving on to the cooling curve is label this entire process as being endo or exothermic, kind of going back to those words that we're using on that first page. And this process, in order to go from a solid to a liquid, to a gas, the substance would have to take in energy. It would have to absorb energy to increase its temperature and increase its spacing. And so we would classify this whole entire process as being endothermic, meaning it's absorbing energy. The water is absorbing energy to move from a solid to a liquid to a gas. So that's the heating curve. Now let's go ahead and move on to the cooling curve. And the cooling curve looks very similar to the heating curve. It's just essentially the opposite. And so we still have our states of matter, except at the very top here to start, we have a gas. That's where the temperature is the highest. Then we're going to start to cool down the temperature. The particles are moving slower, and we're going to have a mixture of gas and a liquid. Then we'll have solely a liquid. The temperature will decrease, 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 and then you have a mixture of a liquid and a solid. And then finally, we are going to have just a solid. Okay, so those are the states of matter at each segment. Next, let's talk about these phase changes. These phase changes are going to have different names because we're not increasing temperature here, we're decreasing temperature. So when something goes from a gas to a liquid, we call that condensation. And that's usually the phase that many students will forget the name of. It's the trickiest one to remember. Condensation, an example of that is when you are working out outside, for instance, or playing sports in the summer, and you have a water bottle. You'll notice if it's really hot out, you're going to see water droplets start to form on the outside of your bottle. Well, those water droplets are gas particles from the air cooling down so much from the temperature of your water bottle that they turn into a liquid on the side of your bottle. And so that is an example of condensation. The next one, when something goes from a liquid to a solid, this is a phase name that many of you are familiar with. This is called freezing. And so liquid to a solid, that phase change is called a freezing point. The last phase change or state change is in something goes straight from a gas to a solid. And sometimes that does happen. That is called deposition. And this also doesn't happen very often, but an example of that is when you wake up in the morning, you go out to your car or your parents' car, and you notice frost on the windshield. That is actually deposition occurring. And what happened was those gas particles from the air became so cold that they formed a solid on your windshield, frost on your windshield. So that is called deposition. Okay, so once again, let's talk about the most important part of this curve, what's going on during each segment with the particles. And let's first start with the diagonal parts of this cooling curve. And at those diagonal parts, the temperature this time is not increasing, the temperature is decreasing. And because at those points the temperature of the substance is decreasing, that means that the speed of the particles is going down, ultimately meaning the kinetic energy is decreasing. So at those diagonal points, because the temperature is going down, the speed is going down, and the kinetic energy is going down. And then at these horizontal points, you can see that the temperature is staying constant. Here the temperature is staying constant at 100, and here it's staying constant at 0. Yet the energy is still being released by this substance. So what energy is being altered here? Not the kinetic energy, but the potential energy. And here the spacing of those particles is not increasing like the heating curve, it's decreasing. The particles are coming closer together, and we once again have a phase change at those points in time, or a state change. And so our particles are going to essentially look the opposite as what they did on a heating curve. Start out as a gas where the particles are really far apart and moving very quickly. And then those particles start to slow down, come closer together, and they will turn into a liquid. And once they're a liquid, they'll slow down more, move closer together, and they'll move so close and be moving so slowly that they will become a solid. And so that's what's happening with this particular substance throughout the cooling curve. And once again, we do have water because the condensation and freezing point is 100 degrees and 0 degrees. Every substance will have different condensation and freezing points dependent on their intermolecular force strength. And then the last thing here will be, let's label this as being endo or exothermic. Well, this time the substance is decreasing its temperature. Energy is being released throughout this process in order to go from a gas to a liquid to a solid. And when energy is released, we call that an exothermic process. When energy or heat is being released. So a cooling curve, or when something goes from a gas to a liquid to a solid, that would be labeled as an exothermic process. Okay, guys, so that's it for today. I miss you. I hope you're all doing well. If you have questions, please let me know before you attempt that Schoology assignment. The answer keys to the written notes are on Schoology as well, so you can view those. And I'll talk to you guys soon. All right, see ya.